So let me also start recording. Okay. So remember last time around we spoke about null states, and we started off showing you, minimal models and what the structure of these uh, structure of the representations would be when we have c less than 1. We found that this had this form of the central charge, and it also had this particular form of the weights of the primaries. And we saw there were several examples. I told you one about the Ising model, critical Ising model, which is c equal to half. And then the fields that you can get, you can figure it out by looking at this particular HPQ. So this actually represents the critical point of a second order phase transition of the Ising model. I encourage you guys to go back and go to the yellow book and try and read this a bit more. I'll only be giving you a glimpse of this, and we won't have time to actually do this much more. But minimal models, there is a whole lot of stuff that you can actually do here. Okay. So that was one, and then there was a tricritical Ising model. There's something called the Potts model, and so on and so forth. This one is not that important. Now you remember one of the things that we tried to do is before this we spoke about null vectors and reducible representations. So then we wanted to give you I wanted to give you a clear idea of what these null vectors are. And for that, we started off at level 2, and we found that you could get, a general state at level 2 was written as 4.56. If we look at chi as a null state, then this has to obey equations L1 and L2 acting on it equal to 0. It, of course, has to obey an equation Ln acting on chi being equal to 0, but for the n's greater than 2, L3, L4, this thing is identically equal to 0. That doesn't give you any extra conditions on H or the central charge. Now, L1 acting on chi equal to 0 allowed us to fix what eta was. And L2 gave us an expression for the central charge, okay? Now, so this meant that if you have a theory with central charge which was given by this, then there was always a null state at level 2 of the form this, right? So this is what we saw. And then what did we do? We looked at the minimal model, that had an expression for, H's and central charges in terms of M. We plugged in, a PQ as, 2 and 1. This is something that will get us a state at level 2. So then we could rewrite M in terms of H if you want, and then you could plug it back into the expression for the central terms that we had earlier. Now, if you do that, you see that you'd come up with the same expression here that you did from our calculation above. This indicates, this proves that for all this minimal series that we had earlier, we would have a null state at level 2. Okay, so this just shows you that this is what is going to happen. Okay, sorry, okay. Now, once we have this, what I wanted to show you even more was how these null states actually help us in understanding the CFT more. To do this, at first we were trying to figure out that what you can do is for any descendant field in your CFT, the endpoint functions of these descendant fields, or some correlation function of one particular descendant field with n other primary fields, can actually be obtained. So any correlation function of fields involving primaries and descendants, or just only descendants, can be understood as in terms of correlation functions of primary fields itself. So if you know what the form of the correlation functions of primary fields are, everything else for you is fixed. So we saw this, and we saw, if you had one particular, if you had one sort of secondary field, which is ln. So this is a descendant that you have here, and there are n number of primary fields. So this is given by this particular differential operator Ln acting on the n plus 1, the correlation function of n plus 1 primaries, where this particular operator has a form like this. Okay, so this means, as I said below here, that correlation functions of descendant fields can be computed from correlation functions of the corresponding primary fields. Very good. Now suppose the descendant field that we chose is this one. If we choose this particular descendant field to be a null state, what does that? What can we get from that? So that is the next thing that we wanted to do. And we have this example of a null state at level 2 that we are going to use. So what does that do? So so the fact that a null state is orthogonal to the whole Verma module translates in this field language to, as I say, the statement that its correlator with any string of local fields is equal to 0. So if you have phi1, phi2 up to phi n, and if you look at this, chi field and take its the correlation function of chi with these n phi's, this has to be equal to 0. Okay, so we are now looking at how this is going to translate into what we do. So so by our previous arguments, so the correlation function of chi with all of these phi's is going to be equal to this particular operator acting on the this n plus 1 sort of correlation function. Okay, phi i's are all primary that we saw before. Remember that if you have a null field, so this was so what is going to happen is that so this chi field is also related to another primary phi in this way. So now you have the n plus 1 point function of primary fields, and you have this particular operator acting on it, like you saw from here, right? Now, the additional thing is that since this is null, the right-hand side of this is equal to 0. So this particular thing gives you a constraining equation. So if you take an endpoint function, this has to obey this relation because of the fact that this field, the chi field is actually null. So the right-hand side has to be equal to 0. So you can translate this into this particular differential equation, 462b. Now what? Now you can suppose that you are looking at something which is phi of omega with, sorry, let me write this down. So you can maybe try to understand phi of, omega with some phi 1 at omega 1, and you know what the form of this is, right? You know that this is c by omega minus omega 1 to the power twice h, and twice h bar as well. Let me leave that aside, when these fields have the same weight. So what you would find is that you can plug this into our formula here, that this operator acting on this 2-point function, what it gives you, and you'll find that it doesn't generate anything new for you. So this is an exercise that you can do. So this is, I mean, trivially true. As I write here, the 2-point function does not yield something new. Now, what you can do, you can take two more fields, phi1 and phi2, and you can plug in the 3-point function, right? So that's what we did last time around. And we found that the 3-point function, so this is the 3-point function. So we plug this into this particular differential equation, and then what we found is this constrains the 3-point function. So if this has to be non-zero, then the h's have to satisfy a certain relation amongst themselves, and that is given by 4.63. Okay, so there is a relation between three fields phi1 and phi2. The weights of these fields have to be related in a certain manner. So just because of the fact that there is a null state at level 2, this requires that any sort of thing, or any sort of any field that CFT that has this null state at level 2, that has to obey uh, the 3-point functions. If they are to be non-zero, then they have to obey a certain relation. I mean, so these weights have to be related in a certain way. What is an example of a CFT that we know that has a null state at level 2? That is all of these minimal series, right? So for which we wrote down the h's in this way. So we wrote down things in this way, right? So what we do now is take h as h112. So that's the state. I mean, that's the null state at level 2. We take h1 to be some arbitrary guy labeled by p, q, and m like before. Then we find that the only things that can appear, again related by this particular relation that we have here, is going to be h p minus 1q or h p plus 1q. What does this mean? This means the OPE of phi 2 with any other primary field phi pq in a unitary minimal model is going to be restricted to lie in either is going to be restricted to lie in the conformal families of phi p plus 1q or phi p minus 1q. This is called a fusion rule, and we did this for level 2, but it can be generalized to higher levels, and you have a sort of more general formula that I've written down here. The form is not that important. The thing that is important is that this is saying that the presence of a null state in your spectrum is actually going to dictate the form of the OPE, if you wish. So two primary fields, their OPEs have to be restricted to the conformal families of certain fields, not all of them, right? So you remember that when we wrote down an OPE between two primary fields, we wrote that the right-hand side was a sum of all possible fields in the CFT. Now we are saying that if these null states are there in the game, the sum over all possible primaries in the CFT is actually restricted, and that can only be a certain. That can only take fields out of the conformal families of certain particular primaries. So this is what the fusion rules of a minimal model are. And I didn't explicitly say this, but I want you to work out this for the m equal to 3 Ising model and see what exactly you get. Okay, so I'll try and put this in your next homework. Very good. So this was fusion rules. What I wanted to do a little bit more is something called a fusion algebra. Now you see what is happening is that, okay, why is this stupid? Okay, very. Now if you have the OP between these conformal families phi I and phi j, this is going to give you some nijk into phi k, right? That's what the I mean, that is what the general form of, if you wish, the fusion algebra is. So now, so these are some numbers which are, I mean, which also include include 0. For, I mean, unitary minimal models, we have just seen that nijk can be either 0 or 1. Okay. So this algebra, this is, I mean, 4.6 is actually sort of, so this left hand side is an OPE, right? So this would mean that it's, I mean, for example, commutative, because of what we learned earlier. So that means nijk is equal to njik. That's one. And I mean, associativity is also there. So that would mean that phi I with phi j phi k is equal to phi I phi j with phi k. Okay. So that would lead to some particular relations between these ends, or you can define some, I mean, matrices, and that will just mean that nink is equal to nkni. This is actually, I mean, this could be of use going forward, and I don't think we are going to reach so far. But I mean, anyway, I wanted to just show you a little bit about what the fusion algebra is and what these things actually mean. So this can be thought of as, I mean, as an algebra in this way. Okay. So that was it for our fusion rules and our fusion algebra. I have a little bit more to say about a few more things before I move on to an example today. And that is crossing symmetry and the bootstrap. So we will have two of you speaking about the bootstrap. I don't want to repeat things that you're going to say, but we'll just, for the sake of doing this, we will see this very briefly. Okay. So what are we going to? So we have seen. So we, as I say, I will address this very briefly. So when we are looking at quasi-primary fields, or I mean, so we have seen what the, I mean, 2-point function or the 3-point function is, right? So I'm writing down both z and z bar out here. Now, okay, just a second. I don't know why. Oh. Okay, now the general form of an OP between two primary fields will take this rather ugly looking form. This is given by this. So you see that I'm summing over all the primaries in the game. This is sort of the general thing. And I have separated out the factors in front of it in a certain way. Okay, so again, I'll not be going into the details of this, but you can separate out factors in a certain way such that you can piece out the things that are only going to be dependent on symmetry. So these parts, these betas and these z factors in front, these are going to be just fixed by, I mean, what your conformal invariance is. Okay. And so what happens is that so the only things that will be left unfixed are these numbers, or you can call these structure constants Cij,P. Okay. Now let me try and just say this a little bit more clearly. So there are these multiple indices. So these k's out here actually label all these, I mean, sort of descendants. So I mean all of these guys. So these are the k's. Okay. Uh, and we will also so so if you wish, you can write down what these guys are. So you can have k1, k2. So these are vectors if you wish. Okay. So these are something that is going to label all of these kns. And you can also write some big K, which is the sum over these ki's. Okay, so the upshot of all of this is that so these betas are also, constants that depend on the central charge of the CFT and the weight of the primary phi p. So as I try to stress, the only unknowns in this whole business are the CIJPs. Okay, the rest of it is fixed by conformal symmetry. So if you are looking at 3-point functions, this is the same as this coefficients that you would have got from the 3-point functions of phi I, phi j with phi k. Okay. So these or phi p, if I wish. I mean, if we so name these phi I, phi j with phi p will just give you these CPIJs. Very good. So that was the general form of the OP. So what do I want to stress? I want to stress that if you give me these CIJKs, these things that I've called structure constants, if you give me the central charge, and if you give me the primaries, weights of the primaries in the CFT, that is, in a sense, fixes your CFT. This is called the CFT data. And this, if you give me the CFT data, that fixes for you a particular CFT. Now I can give you some arbitrary sets of data, right? They might not, all of them might not mesh together. You know, if I give you some random swaths of numbers, that may not be a CFT. Okay, so how do we actually see if a particular set of CFT data is a particular set of data is going to actually sort of correspond to a CFT? So let's see this. So 4-point functions will provide something called crossing relations, which have to be followed for all consistent CFT data. So let's argue this out. So let's look at a 4-point function G, where I have phi I, phi j, phi l, and phi m. And these are at Z1, Z2, Z3, and Z4, okay? As we have seen before, this can only depend on the cross ratios, right? Z1 minus Z2, Z3 minus Z4 by Z1 minus Z3, Z2 minus Z4. Now, so this has to be a function of only x's. I mean, how can you see this? For example, if you want to look at, if you have 4 points by conformal transformations, you can map these 4 points zi to 0, x, 1, and infinity. Okay. Similarly for the z bars as well. Now, this particular function you can actually evaluate in a variety of ways. So remember, you're doing an OPE like thing. So what you can do, as you remember, the ordering out here is not important, right? So all of these things can go through each other if you wish, and these are also not fermionic fields. So you will not also pick signs up. For example, you could first look at the OP of phi I with phi j and look at then phi L with phi m. If you do this, then what is going to happen is that you are going to have some Cij piece and CLM piece, and there will be some other very sort of uh, complicated functions which is going to depend on p's and, as you can understand, x's, and these sort of curly f's which are labeled by ij and lm. These things are what are called blocks. So these are conformal blocks. These again depend on the dimensions of the primary field and central charges of the CFT. So again, what is happening is, except for these numbers Cijks, everything else for you is fixed by conformal symmetry and conformal symmetry alone. These are some weird, I mean, not weird, but there's some complicated functions which you can sit down and find out if you want. Okay. You can also look at this sort of 4-point function, and instead of trying to do this and this, what you can do is you can do this with this and this one with this one. Okay. So if you do that, what is going to happen is this will effectively interchange phi j at z2 with phi l and phi m at z4. This, in a sense, is just the interchange of x with 1 minus x, and everything else goes through. What happens is then this function is given by the following relation of CIMP with CJLP. And now the functions here are going to be functions of 1 minus x instead of x, okay? And the blocks, the labeling of the blocks has also changed. So instead of LMIJ, you have interchanged things. So this is IMJL, okay? So this is what it is. And so as you can see, for example, so you can also choose to, so this, as we said, this was one way of trying to do it. This was another way of trying to do the same thing. Or you can also do this, okay? So if you do that, there is this third way that you will get, and this is the form which you'll get. All of these answers are equivalent. All of these answers are the same. So diagrammatically, if you wish, these answers have to be the same, and this is what you, so this is an infinite set of equations which you are going to get from here. Okay, so this is, so any CFT that is, so you have, suppose you have supplied me with some Cijks, okay? So until and unless these Cijks are actually consistent with this crossing equation that I've pictorially written down here, this particular data will not give you a consistent CFT at the end of the day. Okay, so as I say out here, equality of these three expressions above gives us a number of consistency conditions for the structure constants. These are called crossing symmetry conditions, or the bootstrap equations. Attempting to solve CFTs through this sort of these consistency conditions is what is called the conformal bootstrap program. And we are hoping to hear more about it from a few of your friends here. I think Rishik and Prajwal. So we will learn about it a little bit more when they speak at the end of the course. Very good. So that was that. Okay, that was a bit about the bootstrap. Now, again, this might be a good point to ask me questions if you have them, because I plan to move on to something entirely different. So before I do, let me pause and ask you if you have anything.
Yeah, I
Right.
have this question. Like,
Yeah, please.
you said, like, you can attempt to solve for the CFT data using this
Mm-hmm.
bootstrap equations, right?
Mm-hmm.
Like, is it always possible that given the central charge and the primaries, like you can always determine the all the possible Cij case using this program, or
Now, what is happening these days? So it's easier to do this in. I mean, see, you would remember that what we did is we uh, basically use sort of quasi primaries. Okay.
yeah,
Now, so this same thing can actually go through in, I mean, higher dimensions as well. Okay. Uh, and you can try to attempt to actually bound. I mean, you can try to give these sort of bootstrap like conditions for, I mean, for the higher dimensions as well. In, I mean, two dimensions, things are more, I mean, more sort of restrictive because you have this infinite dimensional symmetry. But the program holds irrespective of you are of whether you are in d equal to 2 or you are higher. In higher dimensions it is harder to do, and people have been sort of resorting to numerics to try and see how much of the, I mean, sort of, if you are looking at the parameter space of all CFTs, what are the things that you can rule out? Okay, so that's what is happening these days. Um, it's an ongoing program. We are trying to understand it more and more. It's not clear, but for the minimal models, you would be able to solve it through this. Okay, uh, this is something that I have not explicitly done, so I can't exactly point you to the reference which would be the best thing. I mean, but so there are these, again, these series of papers by Zamarachikov et al. Um, in the 80s and so on, where they've looked at things like this. I'm not entirely sure if you can find it in just one place, but the answer is that for, I mean, 2D CFTs for C less than 1, the answer is yes. But for, I mean, higher dimensions, I mean, this is a way of, if you wish, sort of ruling out swaths of parameter space and trying to, you know, sort of pin down regions where there can be CFTs and try and look for, I mean, new ones which we don't know, but maybe the bootstrap equation does allow. So this is, I mean, something which is very much in you know, people are looking at it right now basically, and they have been doing this for. So the advent of the bootstrap thing is for these things for higher than d equal to 2 is something pretty recent, and it follows from this work by uh, Richkov, Vici, and others, which is in 2008, I think. Um, and so there's a large sort of program on trying to understand how to actually, I mean, chart out the space of all, I mean, possible CFTs. We're learning more as we speak, and this is
okay,
an active, I mean, active sort of area of research as we speak.
okay. So, like, from your comments, it seems that like the analytical work is like very difficult in d greater
Yeah,
than 2, right?
yeah. I mean,
Yes.
analytical work, you can do it in d equal to 2. For higher, I mean, higher dimensions, it gets pretty hard extremely fast. So people look at certain sectors. You know, if you're you might look at some sectors where, I mean, operators have, I mean, extremely large spin, and so on. So you're looking at simplified limits where you can say more. So that's where we are at essentially. And then you can have some amount of, I mean, analytic handle. But for a more, I mean, for a more sort of general case, people have been following, trying to sort of, I mean, do numerical analysis, and so I mean, analytics are not too great out there still. Maybe it'll all change. Who knows? But yeah,
Okay.
so in two dimensions, the power of infinite symmetries lets you do much more. Okay.
Okay. Yeah. Thank you.
Yeah, sure. Okay, so so we have done a lot of CFT in 2 dimensions, and I thought I would sort of change gear a little bit and show you at least one place where CFTs are actually very useful. And this takes us to the example of string theory. Okay, so what we will do in these next, so the lecture today, and maybe, so there's not much left today, 20 minutes, and we will try and give you a more elaborate run through of things next time around. And the reference, so there are several, I mean, several sort of references for this as well. I'll try and point them out. So any sort of beginning string theoretic book should be good. So I'm not going to do it in, I mean, as, I mean, excruciating detail as one can do it. For example, there's this book by Zuibach which you can have a look at. Zuibach, which is First Course in String Theory. Okay, anyway, so I'll write this down for you later. Okay, so what is string theory? String theory is, I mean, at the moment, the best formulation, I mean, our best framework, if you wish, for understanding quantum theory of, yeah. So you've heard the folklore. So the quantum theory of gravity is what we are after. Why are we after this? We are after this because quantum mechanics. So we want to understand what happens at the smallest of length scales, because the universe is supposed to have begun from a Big Bang singularity, and there are black holes for which there is irrefutable evidence there in the sky now. And we know that Einstein's theory breaks down, right? We know that Einstein's theory breaks down out there. Singularities mean that that particular theory is saying that, look, don't go near this because my yeah, I mean, this particular theory does not work there. That is why there are there are singularities. So general relativity has singularities, and we would expect a quantum mechanical version of them to resolve these singularities. Okay. And the way we do it in string theory is so string theory at the moment is our best hope of trying to understand something like that. What is string theory? So what you do in string theory is that, so for quantum field theory, what you have seen so far is everything is sort of, I mean, point-like, right? Every sort of fundamental thing is point-like. So the interactions are based on points and so on. So fundamental particles are points. What we do is we are going to posit that the fundamental objects are actually not points, but tiny one-dimensional strings. And what we will do is we will input the special theory of relativity and quantum mechanics into the game. And what we'll get as output is a quantum mechanical theory of GR. So So quantum theory of gravity is what we'll get out of it. What do I mean by getting a quantum theory of gravity out of it? I don't know how far I'll be able to go here, but the idea is that if you look at the spectrum of the theory, then what you'll find is that there is a massless spin to object which sits in your spectrum. That is the graviton, if you wish. Okay, so that is what I mean by the fact that you're going to get as output quantum GR. Okay, very central to the success of string theory is CFT and its power in 2 dimensions. And here in the lecture that we in the 15 minutes that we have remaining today and next day, we will examine how CFT actually arises in string theory. Okay, so let's start off simple. We are looking at a point particle, and the point particle moves in space time, and so this is d-dimensional Minkowski space time. As it moves, it is going to trace out this world line. Okay, and this world line is going to be parameterized by a proper time. I mean, yeah. So tau is what I call proper time. So what is the action? As you guys know, the action is something which is the length of the world line, right? So this is going to be integral ds, if you wish. And what is ds? So ds, so whatever, ds squared is equal to minus dt squared plus dx I squared, and so on and so forth. So you can, as you know well, hopefully you can rewrite this. So you can rewrite this in terms of something like this. So x is the position of the particle, x mu. The dot signifies uh, uh, I mean derivative with respect to tau. Yeah, eta mu nu is the space time metric, which is flat, and you have a minus m out here, and you have one puts this in just to make sure that when we look at the non-relativistic limit, it still gives you the usual uh, thing that you would expect, right? So that's how you fix this number in front uh, to be equal to minus m. Very good. So yeah, that's all I was saying out here. The action, as you know, is a measure of the length of the world line. And at first, it appears that this action, so you're in d dimensions, it appears this action has d degrees of freedom, but actually there are d minus 1 degrees of freedom. There are a few ways of trying to see this. Suppose you look at the symmetries of the action. It's obviously invariant under Poincare symmetries, but it's also invariant under reparameterizations of the proper time. So if you can take tau, tau tilde to be some function of tau, you can plug it back into the action, and you would be able to see that the action is actually invariant of how you're going to parameterize it. Okay. Now you can also see that if you look at the action, there is no sort of tau. So tau does not appear with some sort of kinetic term in your action. So tau is not a dynamical variable. So what we have essentially is a redundancy of our of our description. There's also what we also known as gauge symmetry. Okay, for example, you can choose a gauge. So you can choose a gauge of tau being equal to x naught. And if you have tau being equal to x naught, then this very clearly relates x, through x mu, you can just relate x naught with xi, right? So that makes so that's one thing that you need to keep in mind. So even though it looks like that your particle has d degrees of freedom, actually it does not. things are actually related. Another way to look at the same thing is you can look at the Lagrangian, and then you can look at what the generalized momenta are. You can find this out, and then you can find out what the Hamiltonian of the system is. And lo and behold, you'll find that the Hamiltonian is equal to 0. What is this? This vanishing of the Hamiltonian is a sort of a consequence of the reparametrization invariance. And this is just saying that, p squared plus m squared equal to 0. This is the mass, this is the Marshall condition. It's just saying that a particle has to move in a time like direction or a null direction. If m is equal to 0, then it moves in a null direction. But so the number, so this particular constraint that you have on your system decreases the number of degrees of freedom from d to d minus 1. Okay, very good. Now see that we have an action. Okay, so what do? So you write down a classical action, and then you want to go to a quantum mechanical version of this action, right? Now you have a square root, and a square root is not the best thing to do, best thing to have if you want to sort of start to quantize a theory. So let's see if we can get rid of the square root, right? So what we will do is we will add a fictitious field, and we will call this fictitious field E. So we will add an E inverse here and an E here. Okay, this is called the Einbein. And so if you find out what the equations of E are, so then it just becomes x dot squared plus E squared m squared equal to 0. This fixes E. And what you can do is you can plug this equation of motion into this action here. And it's a simple exercise that from this action, you can also get to the square root action. Okay. Notice another thing. One more thing that is important here is that suppose you wanted to look at a point particle which is massless. You have mass which sits out here, right? So this particular action again is not very suited for trying to take some sort of massless massless limits. On the other hand, now the action that we have found has m square which sits here. So you can happily just take the m goes to 0 limit as well. It also, of course, does not have the square root, which we wanted to get rid of at first. So we have a nice action. Okay. So so this is a nice looking action. And as I said out here, so apart from getting rid of the square root, we have also brought m squared to a place where the m going to 0 limit can be appropriately taken. And you can now perform massless limits without any problems. What are the symmetries of this action? For again, you can show that Poincaré's symmetry of the space-time will be preserved, as will reparametrization invariance. And this again, you could work out. So what happens is under infinitesimal reparametrization, tau goes to tau plus xi of tau. Del E will transform in this way, del X will transform in this way. You can plug back 5.7 into your action, and you can show that this is invariant. Very good. So this is the point particle with which I hope you are reasonably familiar. You might not be familiar with the last action, but I would. So this is pretty straightforward. And we are going to use a very similar thing for the string as well. So let me just lay this down to you, and we will go through it again next time around in more detail. Now, what do we want to do? We want to move to strings. So from point particles, now we have moved to strings, and we will take closed strings. So strings can be open or closed. Okay. So here we are going to be looking at closed strings. So okay. So as a string moves in space time, remember a point particle swept out a line. So if it's a string, it is going to swipe out. It is going to sweep out something which is going to be a two-dimensional surface, and we'll call this a world sheet. Okay. A world line you sort of parameterized with a single coordinate tau. Now we are going to parameterize this world sheet with two coordinates. We're going to call it sigma and tau. Okay. In short, we'll call it sigma A. Remember that the action of the world line was the length of the world line. Okay. So for the world sheet, this is again going to be the area swept out by the world sheet. So this is simply just d2 sigma times the square root of gamma, where gamma is the metric which is induced on the world sheet, right? So for example, if you are trying to look at a volume of something in d dimensions, that is just integral ddn and ddx of square root of minus g, right? So that's always the case. Now, so if this is going to be what our action is, so in this case, this is very simply just d2 sigma into a determinant of gamma, where gamma is the induced metric on the world sheet, and this is just given by the pullback of this the flat metric onto the world sheet. So this is del A x mu, del B x nu into eta mu nu. And you can write this particular guy in terms of x dots and x prime. So remember, x prime is just del x del sigma. Okay. If this is not clear to you, I recommend that you look at, for example, Zweibach's book, and he does this in a great amount of detail, and should be extremely easy for you to just follow that. Now, so what are these x mu's? X mu's, like for the point particle, this is the position of the string in space time. Now notice that it only has this mu dependence. It does not have any a dependence. So it's a scalar on the world sheet. Okay, it's a vector in space time, but it's scalar on the world sheet. We are going to keep these small ab's as our indices on the world sheet, and mu's as the indices in space time. Very good. Now what? Just like the point particle action, our Nambu-Goto action. So this action is called the Nambu-Goto action. Okay, so these are two people who discovered this. So NG means Nambu-Goto. So just like our point particle action, the Nambu-Goto action is also invariant under Poincare symmetry, and there is also a reparametrization invariance. Okay, under world sheet world sheet diffeomorphisms, this is again going to be, the action is again going to be invariant. This is a gauge symmetry, and the degrees of freedom will now be d minus 2. You can show that using so you can also show that as an artifact of the diffeomorphism symmetry on the world sheet, the Hamiltonian is again going to be 0. I'll actually set this as a homework for you guys to show that the string Hamiltonian goes to 0. But we are nearly at the end of the class, so let me just say how this goes. Again, this is an action which has a square root, right? This is an action which has a square root and it has a t in front of it. So it has the same sort of problems like we had in the point particle action. So we want to get rid of the square root. What are we going to do? In order to get rid of the square root, we are going to introduce another field into the game. Okay, we will work on this more. But what happens is that this field is going to be the intrinsic metric g alpha beta, and so this is the action that we are going to use. This is called the Polyakov action, and you can show in a very similar way that you showed for that. I mean, we just indicated for the the point particle action, that the Polyakov action and the Nabu-Goto action are one and the same. So you take the equations of motion of GAB, plug it back into this action, and you're going to get the square root action out. Okay. So this again will be will be another homework, but yeah. So just notice here that the GAB does not have any sort of kinetic terms in the action. So its equation of motion that it will have, these are going to be constraints in the theory. Okay, so that means that if you find out what TAB of the system is, this is identically going to be equal to 0, and this is going to be what is going to be the constraints of the system. All right, so to cut a long story short, we will do this in much more detail as you go forward. We will see that this particular action also has some gauge symmetries. We will fix a gauge in which we can fix this action becomes simpler. But even after fixing this gauge, there'll be some symmetries which are left over. Those symmetries which are left over, interestingly enough, give you two-dimensional conformal invariance on the world sheet. We will see this explicitly next time around. But 2D CFTs arise on the world sheet of the string after you have fixed a gauge. This particular, sort of manifestation of symmetry here is going to be as residual gauge symmetries. We will see this in much more detail, but that is where conformal symmetries show up on in string theory. So you take this, the string world sheet. There is an action for the string world sheet. This is particularly the Polyakov action. You fix this has gauge invariance, so you fix a gauge. Even when you fix a gauge, there is some sort of symmetries left over. These symmetries are going to dictate how you are going to arrange, for example, the whole theory of these relativistic strings. And this is where CFT is going to be absolutely fundamental to the whole thing. That was a quick overview of what we're going to do. We're going to try and pause and go through this in more detail next time around. Okay, but if there are some questions, I can address them right away.
Yeah. So I have this question.
Yeah, please.
So this residual symmetry is like this analogous to this, like when in path integral quantization of gauge theories. Like once you fix the gauge by the Fadi-Popo procedure, like you'll have this leftover BRST symmetry, right? The remnant.
Yeah, we are not going to do the same thing. You can do an equivalent thing in the string theory case as well. At the moment, this is more like if you have looked at QED and you have looked at the Gupta broiler like formulation, right?
Yeah.
There you have to. So what is going to happen is that you are going to if you look at this action, and if you take this GAB equal to just being flat, okay, so this just then will reduce to an action which is just simply this is your simple action, right? It's supposed to be a sort of, simple scalar field, right?
Right,
That's,
right.
just n of them.
Yeah,
So you know what to do for this, right? For field theory, for some free scalar field theory, you always know how to go about doing this.
right.
But not only that, you also have to keep in mind that when you quantize the system, you have to impose something else. Your constraints will also have to be imposed on this. So this is how we are going to actually look at that, in the sense that we are going to have a notion of physical states in the game. So only those states will be called physical. Those are which will actually give will be compatible to the constraints of the system. So even though this looks deceptively simple, it's not as straightforward. Again, it's sort of like the Gupta-Broiler way of doing things. So you impose something on this Hilbert space itself. Okay, so you rule out certain states as being unphysical. What you
Okay,
were saying about the BRST quantization is something that can also be done in string theory, but that's not something that we are trying to do at the moment. We're just doing sort of canonical quantization at the end of the day. As you can well understand, it can all be reformulated in a path integral form as well, of course.
okay, okay.
Okay.
Yeah. Okay, yeah.
But more of this as we go on. Okay.
Yeah, yeah, sure, sure.
So any more questions? Is this becoming a little too heavy? If you guys think it's becoming a little too heavy, let me know, okay? So if not, the idea at the moment is I'm going to give you another lecture on the string theory case as our example. Show this to you a little bit. Then we will move on to the torus, and I'll give you some amount of modular invariance and so on. And that is going to, I don't know how many lectures. We might have one extra lecture next week, maybe Thursday or Friday or something like that. And so then we will see how we feel about it. And I want to do a little bit of holography at the end to wrap up things, but let's see how we can, how far we can go. It would have been good to get a few more lectures, but that'll always be the case. I'd want some more all the time. Does that sound reasonably okay to everybody? Okay. Silence everywhere today, except, yeah, protection. Nobody else is quite speaking today. All right. If you have any sort of things that you would want me to have say a bit more about, please drop me an email or say so now or sometime in the next few lectures. Yes, please.
Sir, how much, sir? I mean, what topics of holography are you planning to do?
No, I was just thinking that if at least I could show you that symmetries match. You take ADS and you look at the symmetries of ADS, and I'll show you that in that is going to match to the things that we have been trying to do, and that would be a nice way to sort of end things, I guess. Of course, I can't even begin to do holography. That would be at least another course. Yeah. But yeah, so the idea is I will go to the torus and I will show you, there is something called a Cardi formula, which I wanted to do. I will try to do that. And maybe if time permits, which I don't think it will, there is a very nice, cute thing that you can actually do in holography, you can show that this I mean, Cardi formula is also something that reproduces the I mean, so the Bekenstein-Hawking entropy of black holes in ADS3. That would have been my ideal sort of place where I would have ideally liked to stop. But let's see. I mean, I don't want to rush things. So let's see. I mean, so let's see how far we can go. Okay. That's the idea. Maybe I can give you guys a few more things to read. It doesn't have to end if you guys are you know are interested in trying to read a little bit more as well. So that's the idea. That's the idea. Yeah. Let's see how far we can take this. Okay. Okay. Any more questions, comments, or you know, the requests for what you want to learn or what you don't want to learn, or so on?
Sir, will the Witten diagrams be relevant? I mean, will we be doing this?
Witten diagrams are a little that will be a bridge too far.
Okay.
That'll be a bridge too far. Yeah, maybe. Yeah. So yeah. That I mean, I would have liked to do them, but unfortunately, yeah, that's going a little bit too far. Maybe when you yeah. I mean, I know for what you are attempting to do, it would have been very nice if I could.
Yeah, actually, I can't decide even if this is at my level or not. These things.
No, Witten diagrams are a little complicated actually. So yeah, I mean, have fun. Don't be. I mean, you know, try and see how much you can understand. I understand that some of the things that you guys are attempting to do are hard. It's all right. Okay. So try your hand at it, because usually one needs to do a lot of the background work to get to these the papers that you're trying to read. So if you cannot understand something, only thing that I would like to say for the final things that you guys are going to give us is that try and make sure that the little bits, you know, even if you do not understand most of the things, that's not that's not material. Be honest and say that I could do this and I work these things out. Rest of these things I don't know. I would plan to do this and so on, or you would read. But for the sake of the project, just make sure that the things that you write down and the things that you say you have done, you have actually done. Okay. And if there is a lot of jargon, try and keep things as simple as you can. And you know, there is enough new things around everywhere, so that you would be able to say say things. And in now, if you are stuck with something, if you want some more clarity about something, or you want to ask me something else, please drop me an email and we can have a chat. Okay. All right, so that's it for the day, and we will meet again day after tomorrow, and I'll try and upload the notes sometime soon. Okay. There'll be another homework coming to you at the end of this week. Okay, guys. All right then. Let me stop recording first.